Dear students, welcome back to the GATE training course on mechanics of materials. This is lecture 2, plane stress, plane strain and principal stresses. I am Professor S. Pradesh Murthy, Assistant Professor GCT Coimbatore. So today's topics for discussion: three-dimensional stress system, plane stress, plane strain, principal stresses and principal plane, maximum shear stress. Right. So let's start with the three-dimensional stress system. So let us assume a rectangular block with x-axis, y-axis and z-axis as shown here. So due to the external loading, it is acted upon by a stress, normal stress sigma x along the x direction and sigma y along the y direction and sigma z along the z direction. So these are the normal stresses, right? So what this normal stresses do is it tends to pull the material away. That is, it tends to extend the material along the x direction, y direction and z direction, since the direction shown is away from the material, right? And in addition to that, we have shear stresses, that is tau xy, tau yz and tau zx. As a result, it tends to shear the material, that is, it causes angular deformation on the material. So the deformation caused by the normal stresses will be Ex, Ey and Ez. We call it as normal strain, and due to the shear stresses, the shear strain gamma xy, gamma yz and gamma zx will also occur on the system. We have to clear one thing. Say we are assume we are applying only a load along the x direction. As a result, we know along the x direction a tensile stress will be acting. So even though we are applying stress along only one direction, what happens, as we have discussed in the earlier classes, when we are applying a load in one direction, in the other two perpendicular axes, if elongation happens along the x direction, compression happens along the y and z direction. That is, lateral strain occurs in the other two directions. So as a result, even when you are applying a stress along one direction, the other stress components like sigma y, sigma z, tau xy and tau yz and tau zx, it normally happen in a system. So whatever may be the loading, in every case, every system is three-dimensional stress system. Okay, now come to the next point. Okay, so due to this stresses, three-dimensional stresses, say assume we are having three stress, sigma x, sigma y and sigma z. Let us have the equation for strain along the x direction, that is normal strain along the x direction, that is Ex, which is equal to sigma x by E minus mu into sigma y by E minus mu into sigma z by E. As I said before, due to the stress along the x direction, there will be elongation along the x direction, right? So this is a term. And due to the y stress along the y direction, there will be a reduction in length along the x direction, that is the lateral strain. If you are elongating along the y direction, along the x and z direction, there will be reduction in length. So this there comes a negative sign here due to the reduction of strain caused by the lateral strain occurring by sigma y, and similarly for sigma z. So for E y and Ez, we have the corresponding equations as sigma y by E minus mu into sigma x by E minus mu into sigma z by E, whereas Ez is equal to sigma z by E minus mu into sigma x by E minus mu into sigma y by E. So that is, the linear strain component will be positive and the lateral strain component will be negative. Okay. Now similarly for tau xy, we can relate it to the gamma xy, that is the shear stress and the shear strain, by the rigidity modulus. We know that shear stress by shear strain is equal to rigidity modulus. So shear stress tau xy is equal to G into gamma xy. Right. Similarly, tau yz is equal to G into gamma yz, and tau zx is equal to G into gamma zx. So where E is Young's modulus, mu is Poisson's ratio, and G is modulus of rigidity. Now, so we can solve every problem as a three-dimensional problem, even when there is one directional stress or two directional stress or three directional stress which we are applying, three-dimensional loading which we are applying. We can solve the problem as a three-dimensional problem. There is no problem, what you can say, no difficulty, or there is no nothing prevent you from solving the problem in a three-dimensional way. But solving the problem in a three-dimensional manner is tedious. So as an engineer, we think of a different way. Can we make the problem simpler? Okay. So as a result, we come across two concepts. One is plane stress and another one is plane strain. Right. So in plane stress, what we are doing is the stress components along one of the axis, normally z axis, is considered as 0. That is, instead of making it as a three-dimensional problem, solving it as a three-dimensional problem, what we are doing is we are going to solve it as a two-dimensional problem. So what we are doing here in a plane stress condition is we are making the stress components along the z direction as 0. So that is a plane stress condition. So if we consider the strain along the z direction as 0, then the condition is plane strain. So now in plane stress or plane strain condition, the problem will become a two-dimensional problem. So in the plane stress condition, you are not going to worry about the stress along the z direction. In the plane strain condition, you are not going to worry about the strain along the z direction. That's it. So now we can move on to what is plane stress and what is plane strain. So as I said before, so sigma z, that is the normal stress along the z direction, as well as the shear stress components tau yz and tau zx is equal to 0. We are considering the stress along the z direction to be 0. Okay. For what kind of problem we can assume it to be a plane stress condition? Say assume we have a rectangular plate where the length, that is which is marked along the x direction, as well as the height which is marked along the y direction, it is more and the thickness is small, right, and it is fixed at one end and it is loaded with some loading at the free end. So these kind of problem, we assume it to be a plane stress. Why we are assuming it as a plane stress is we are not restricting the material along the z direction. See here, it is free to move along the z direction. Along the z direction, we are not constraining it. It is free to move along the z direction. So here, since we are applying the load either along the x direction or y direction, the stress along the x and y direction will be more, and the stress along the z direction will be very, very negligible, since we are not constricting or which we are not fixing the z direction. So the stress component which is developed along the z direction will be very, very negligible. So these kind of problem where the length and width is more and we are not constricting the other side from prevented the other side from moving, so we can say It is a plane stress problem. So these kind of problem we solve as a plane stress problem. Okay, now so these are the equations which we have derived earlier for Ex, Ey and Ez, right? So now what we have assumed now is sigma z is equal to 0. So the component which we have, which is highlighted here in a red rectangle, we can remove it. Since sigma z is equal to 0, so this term goes out, so it becomes Ex is equal to sigma x by E minus 1 by m into sigma y by E. So remember, 1 by m is Poisson's ratio, or we can say mu. Mu and 1 by m is both are one and the same. So here Ey is equal to sigma y by E minus mu into sigma z by E minus mu into sigma z by E, which is equal to, now this term gets cancelled. So we have got another 3 set of equations. So now what we are doing is, from this equation we are going to solve these two equations, equation 1 and 2, modified equation 1 and 2, and we are going to find an expression for sigma x and sigma y. See here. So by solving those two equations, modified equation 1 and 2, we can get sigma x is equal to capital E, that is Young's modulus, into Ex plus mu Ey by the whole by 1 minus mu square. Similarly, for sigma y is equal to capital E into Ey plus mu Ex the whole by 1 minus mu square. So this is the normal stress developed along the x direction and the normal stress developed along the y direction due to a plane stress condition. So this is the equation for it. And similarly we can relate, already we have the fourth equation, tau xy is equal to capital G into gamma xy. So now you can say, already we have written the equation Ex is equal to something and Ey is equal to something. What is the need for solving and finding the equation for sigma x and sigma y? Right? Let me go back. Say this is the equation for Ex, this is the equation for Ey. What is the necessity for solving these equations and finding sigma x and sigma y? Right? So the problem is, in any engineering problem, what we do is, we may be having a system or we may be having a structure. On that structure, we will be applying the load, external loading. So due to that load, what happens? A stress is developed internally, and at the same time, strain occurs, right? That is, displacement occurs. So what we can do is, we can measure what is the external loading. At the same time, we can measure what is the end effect, that is the displacement. But measuring the stress is very, very difficult. So we have methods for measuring stress, but measuring stress is very, very difficult. So what we do, we measure the external loading and we measure the displacement and then convert it as strain component, and from the loading and strain we calculate the stress. Okay, so from Ex and Ey, finding sigma x is easier. So that's why we have solved these two equations and we are writing the equation for sigma x and sigma y. Now we can go on to plane strain condition. So in the plane strain condition, as I said before, we are considering the strain along one direction, normally along the z direction, to be 0. That is, the normal strain Ez and the shear strain gamma yz and gamma zx is equal to 0. This is the assumption. Now we can think about for what type of problems we can consider it as a plane strain condition. A suitable example is shown here, a schematic sketch. Assume we have a dam, right, and the x and y direction is shown here. This is the x direction and this is the y direction, right, and this is the z direction. So normally a dam, a gravity dam, right, it will be constructed between two rocky region. So assume this is a rock and this is a rock, and between this a dam is constructed. So gravity dam holds its position by its own weight. So due to its massive weight, it keeps the structure intact, right? So what happens, this is the water pressure. From here water pressure is acting on this side. Okay, so what we are doing is, since we have constructed it between two rocky region, it cannot expand along this direction, that is Z direction. It cannot deform or it cannot expand along this Z direction. So the strain along the Z direction is arrested. But whereas due to the pressure, it will buckle along the Z direction to a little bit. Okay, and due to the weight, it can go down by a small value, but it is not allowed to move along the Z direction. So this type of problem we can assume it to be a plane strain problem. So now we can convert the analysis of a dam structure from a three-dimensional case to a two-dimensional problem, right? So now come to the previous equation for plane strain. Previously we have removed sigma Z component, but now we cannot remove sigma Z component. Instead, what we said is Ez is equal to 0. So this is the equation for Ex, this is the equation for Ey, and this is the equation for Ez, and we are equating it to 0. So now we have three equations, right? From these three equations we can solve it and we can find the equation for sigma x and sigma y. So we can solve these three equations and we can find sigma x, sigma y. And remember, as per our definition, sigma z is not equal to 0. So sigma z is not equal to 0, but we have not written the equation here. But since we are applying load along the x and y direction, the stress along the Z direction will be there, but it will be very small. So we are not considering it. Normally we will not consider it. So sigma Z is also there. Okay. So by solving this, we can find the equation like this. So this is the equation for plane strain problems. So here also we are finding sigma x, sigma y and tau xy. Remember why we are finding stress? Because it is easier to measure the load and the strain, and it is difficult to measure the stress. So we are keeping the deriving the equation for stress. Okay, now let's move on to the next topic. For a plane stress system at different plane, what are the value of sigma n and sigma t? What is the value of normal stress and tangential stress, right? That is what we are going to show you. So now we have a two-dimensional stress system. Assume it is a plane stress system. We have a rectangular block and we have sigma y acting along the y direction and sigma x, that is the normal stress component along the x directional sigma x. This is the stress acting on the material. Now consider a plane which is inclined at an angle phi from the plane y, right? From the vertical plane it is inclined at an angle theta. So along this plane we will be having some stresses acting over it. We can again convert this stress, or we can resolve the stress acting on it in a direction normal to this plane as well as tangential to this plane. When a stress is acting normal to the plane, we call it as a normal stress. When it is acting tangential to it, we call it as a tangential stress or shear stress. So even though the loading which is acting exterior is purely normal stress acting sigma x and sigma y along the x and y axis, but when we are considering an oblique plane which is inclined at an angle theta to the vertical plane or to the y plane, along this plane we will be having normal stress and shear stress. So now we are going to find the equations for calculating sigma n and sigma t at an angle theta with y. So I am not going to have a detailed derivation of this. That is not theme of the work. We have to just refresh the concept and we have to go on to solve the problem. So this is the final equation which we have derived for sigma n, that is normal stress. So that is the equations says like this: sigma n is equal to sigma x plus sigma y by 2 plus of sigma x minus sigma y by 2 into cos 2 theta, where theta is the angle from the vertical plane or from the y plane. Remember this, the angle is measured from the vertical axis. So this is what we have derived. So we have a detailed derivation, and from that this can be derived. And then similarly for sigma t, the equation says it is sigma x minus sigma y by 2 into sin 2 theta. Now let's come to a point. What is the significance of finding the sigma n and sigma t? Say what happens? Say assume, as I said before, see here, in this plane, assume we have sigma n here and sigma t here, right? What happens when sigma n acts on a plane? It is more like a tensile stress, right? It assume we have different molecules or different grains over here. The sigma n tries to pull the material apart, that is, it tries to move it away, more like a tensile stress. So sigma n acts like a tensile load, whereas sigma t, it is a shear stress, right? So just the grains which are above the plane and below the plane, look at it here. So this grains just above the plane will move towards the left, whereas the plane which is that is grains just below the plane will move towards the top. So due to sigma t, the component will fail by shear, but due to sigma n, the component will fail either by tension or by compression. So this is the idea. So let me put it in a different way. Assume this material, this is made up of some material which is capable of withstanding 100 unit of tensile stress, right? So it is capable of withstanding 100 unit of tensile stress. Assume along the x direction, that is sigma x, I am applying 70 units of tensile stress. So along this direction I am applying 70 units of tensile stress, and along y direction I am applying some 50 units of tensile stress. Okay, so along x direction 70 and along y direction 50, and the material is capable of withstanding 100 units of tensile stress. So in neither the direction you haven't exceeded 100, right? Along one direction it is 70 and along the other direction it is 50. In neither of the direction it has crossed 100, but there is a possibility that due to the combination of these two normal stresses, in some other plane there may be a stress which may exceed 100 units of stress normally, say along some oblique plane like this, due to the action of 70 units of direct stress or normal stress and 50 units of direct stress along the y direction, more than 100 units of normal stress may be acting along this plane. So what happens, even if you are applying a stress which is much lower than 100 units of stress which the material is capable of bearing, there may be in some direction there is a possibility of developing a stress, normal stress, which is more than the bearing capacity of the material. As a result, the material will fail in tension along this plane. That is, it may develop a fracture in this direction due to tensile loading. So this is one case. So similarly, you haven't applied any shear stress, but due to the combination of this loading, it may develop shear stress. It will develop shear stress. And in some other plane, the shear stress may go beyond the permissible bearing shear level of the material. Say assume the shear stress, maximum possible shear stress of the material is 40 units. So you have applied normal stresses of 70 and 50 along x and y direction. So you say as a result, it may have crossed 40 units in some plane, 40 shear stress units in some plane. So as a result, the material may fail in shear in that particular plane. Right. So that is the reason for finding sigma n and sigma t. Due to the combination of various loading, it develops different values of sigma n and sigma t in different planes, that is in different inclinations. As a result, in any of the plane, if in any one of the plane, if it either exceeds the sigma n limit or sigma t limit of the material will fly. So for assessing this, we have different failure theories. This is not the scope of study here, so we can limit it with this discussion. We can then proceed forward. Right. So now we can go for sigma n max and sigma t max. In the previous equation, you might have seen sigma n. So this is the equation for sigma n into cos 2 theta. So for this to be maximum, this value has to be 1. Cos 2 theta has to be 1. So cos 2 theta so will be maximum when theta is equal to either it has to be 0 or theta has to be that is 2 theta has to be 180, right? Cos will be 1 at 0 and 180. So when theta is equal to 0, cos becomes cos 0, so cos 0 is 1, and when theta is equal to 90, it becomes cos 2 into 90, that is cos 180, so again it is maximum. So sigma n will be maximum at theta is equal to 0 or 90 degree. And sigma t, this is the equation for sigma t. So for this to be maximum, sin 2 theta has to be maximum, that is sin has to be 1. Sin 2 theta has to be 1. So sin will be maximum at 90 degree. So sin 2 into 45 degree, that is, so it will be maximum at either 45 degree or 135 degree. Okay. So this is the condition for the maximum sigma n max and sigma t max for a plane stress condition where the stress acting is normal stress along the x direction and normal stress along the y direction. Now come to the next case. What we have here is we have sigma x and sigma y along x and y direction. The same time we have the shear stress component tau xy also acting on the plane. So now due to this, in the same manner we can derive sigma n and sigma t values, where sigma n is equal to sigma x plus sigma y by 2, and sigma x plus sigma y by 2 plus of sigma x minus sigma y by 2 in the cos 2 theta, which is the equation in the previous case, plus of tau xy sin 2 theta, right? And similarly sigma t, which is equal to sigma x minus sigma y by 2 in the sin 2 theta, which is the sigma t equation in the previous case, minus tau xy cos 2 theta, right? So when there is only two normal stresses, we can directly say that this is the angle at which the value is maximum. But here we cannot say at which angle it will be maximum. Okay, so we cannot say at which angle is maximum. The maximum value sigma n and sigma t value will be maximum depending upon tau xy. So depending upon tau xy, this will vary, right? So now we can go to the next topic, that is principal stress. So first we have to understand what is a principal plane. This is a plane at which the tangential stress or tau is 0. Remember here. So at the plane, so we have seen oblique plane. On that plane we have derived the equation for sigma n and sigma t. We have said what is sigma n and what is sigma t, what is the importance of sigma n and sigma t. So now in a plane at some angle, when sigma t or tau, right, in some books it will be referred as tau. So sigma t or tau is 0, that is there is no shear stresses. When you are moving the plane along some angle, and at some angle the shear stress component will be 0, that particular plane is called as principal plane. So the value of normal stress at the principal plane is called as principal stress. So sigma n in that particular plane is called as principal stress. So remember, at that particular plane there is no sigma t, only sigma n. That sigma n value we call it as principal stress. Two principal planes occur for a plane stress system, maximum principal plane and minimum principal plane. So we will be having two planes. In that two planes the shear stress will be 0. So we can say we have two principal plane. So on one principal plane the stress will be very high, that is sigma n will be very high, and in the another value sigma n is lower. So we call it as the maximum principal plane and minimum principal plane. So the stress is maximum principal stress and minimum principal stress. So at maximum principal plane and minimum principal plane, the principal stresses are maximum and minimum respectively. So we now know about principal stress. That is at principal plane only sigma n is there. So and we call it as the principal stress. Okay, now let's have this diagram here and we can discuss now. So we want to find what is the angle, what is the plane, what is the location of the plane at which this principal stress occur. That is, we want to locate the principal plane. The formula for locating the principal plane is tan 2 theta p is equal to 2 tau xy by sigma x minus sigma y. So theta p, this is the angle of the principal plane. So that is this oblique angle of the plane at which the sigma t is equal to 0 or sigma n is maximum or minimum, right? So now we have two options. We can find tan 2 theta p. We can find this by equating sigma t is equal to 0. That is, at this particular plane sigma t is 0. So we can equate the sigma t equation to 0. Thereby we can derive this value. Or otherwise, at this plane, sigma n is maximum, right? So we can differentiate sigma n with respect to theta. Okay, d sigma n by d theta, and we can find the value of theta. That is, at that value, the stress sigma n value is maximum or minimum. So either by these two methods, we can derive the equation for finding the position of principal plane. So this is the equation, where theta p is the principal angle. So this is the angle measured from the vertical axis, y axis, remember that. Okay, so now we have two principal stresses. So sigma p1, we call it as the major principal stress or the maximum principal stress. It is written by the expression sigma x plus sigma y by 2 plus root of sigma x minus sigma y by 2 the whole square plus tau xy square. And similarly for sigma p2, so it is mentioned as sigma p1, actually this is sigma p2. Please pardon me. So this is sigma p2, which is equal to sigma x plus sigma y by 2 minus root of sigma x minus sigma y by 2 the whole square plus tau xy square. So here it is plus and here it is minus. So now at any plane, so we know that at the principal plane there is only sigma n, there is no sigma t. At any plane, some other plane, there will be sigma n as well as sigma t. So we can find sigma n and sigma t using the relation for sigma n and sigma t. And we can find what is the resultant stress. So normal, the value for resultant stress, sigma r is equal to root of sigma n square plus sigma t square. So this resultant will be acting at some angle with sigma n. Right, so from the normal to the plane, so this is the normal to the plane, assume this is the normal to the plane, the resultant stress will be somewhat acting something like this, assume like this. So the angle from the normal, we call it as the obliquity or phi. So angle between resultant and the normal of plane. Now remember, I have put an equation here which is highlighted in yellow color. Sigma p1 plus sigma p2 is equal to sigma x plus sigma y. That is, the addition of major principal stress and the minor principal stress is equal to the sigma x plus sigma y. That is the normal stress acting along the x direction as well as the y direction, whatever may be the value of tau xy. Sigma p1 plus sigma p2 is equal to sigma x plus sigma y. Remember this. This relation will be very useful for saving time. We can see that later. Okay. Now, as I said, along the principal stress or along the principal plane, the sigma n is maximum. So now, when you are moving the plane or when you are rotating the plane at some other position, the value of shear stress will be maximum. So we call that plane as plane of maximum shear stress. So we can identify that at maximum shear plane, that is, it is a plane at which the tangential shear stress or the tau is maximum. Maximum shear plane occurs at an angle 45 degree from the principal plane. Remember this. This is again an relation which is going to be very useful. For finding the shear plane, what you have to do? You have to find the principal plane and just add 45 degree. Always the shear plane acts at 45 degree from the principal plane. So theta tau max is equal to theta p plus 45 degree. That is, theta tau max is the angle at which maximum shear occurs. So sigma t max, so r we call it as tau max is equal to sigma x minus sigma y by 2, right? So with this I close this lecture. So let me sum it up. What we have seen here is three-dimensional stress system. Let me go to the plan of my lecture and let me sum it up. Three-dimensional stress system. What we have discussed is what are the types of stresses acting on it, the normal stresses as well as the shear stresses. So we have derived an equation for Ex, Ey and Ez, and from that we have derived equations for sigma x, sigma y and sigma z. Right. And then we have seen what is plane stress and what is plane strain. What is the need for plane stress and plane strain? Why when we are considering it as a plane stress problem and when we are considering it to be a plane strain problem. And then we have seen about the principal stresses and principal plane, that is at some plane there will be only normal stresses, we call it as the principal stress, right? In some other axis the shear stress will be maximum, we call that as maximum principal, that is maximum shear stress plane. So these are the things which we have discussed. Thank you.